Well, here it is. We'll give our first proofs. We learned in the previous section how to set up a proof. So here in this section 3.3, we'll set them up, and then we'll do the second part, the second and most important part. That is, we'll actually prove the theorems. Okay. So before we hop into that, we'll have to talk a little bit about what proof is. And if you think back to the work that we did in chapter 2, I think that you'll find this a familiar notion. And then once we talked about what we mean by proof, we'll give our first proofs. We'll prove, for instance, and I think this is the best proof of the section, that vertical angles are equal to one another, that and others as well. So remember how we set up a proof. That is what proof structure is. We did that in the previous section. If necessary, and we'll usually do this here at the start, write the statement to be proven in conditional form. If necessary, draw and label a diagram, and that's almost always necessary in this class, since it is a geometry class and we can draw diagrams to illustrate what we wish to prove. After the diagram, we state the given of the proof and what we wish to prove, and we make them refer specifically to the diagram. And then here's what we'll learn how to do in this section, or begin to explore anyway. This is a difficult problem, really. We'll begin to develop proofs of conclusions. Okay. So what is a proof? And I suppose this is the central definition of the entire class. What does it mean to develop a proof? What is that which we have developed? Well, here it is. A proof is a sequence of statements that takes us from the given to the conclusion. Okay, so that's the first part. Each statement must be justified, all right? And it must be justified by reference to a definition, a postulate, or a theorem that's previously been proven. Okay, so think back to what we did in chapter 2. Okay, remember those tables that we produced, right? Remember that they did have two columns. All of them, sometimes we inserted a third column, but they all did have two columns. Those columns were statements, or sometimes called claims, and the by column as well. What comes into the by column is the justification for each new step that we make. Now, in that previous chapter, chapter 2, in the by column, it was always some definition or some postulate. But here, what we'll start to do is this. We'll start to prove theorems. And once a theorem has been proven, then in the proofs of later theorems, we can make use of that, the name of that theorem in the by column. So once a theorem has been proven, it becomes a rule that we can use to justify steps that we make in later proofs. So here it is. Okay, so what is a proof? It's a sequence of statements that takes us from a given to a conclusion, where every statement that we make is justified by some definition, postulate, or a theorem that's been previously proven. Okay, so that is, we will produce tables that have a statement column and a by column, and also typically have a from column as well. So column or paragraph, well, usually column style, that is table style. I'll use those terms interchangeably. Later on, we'll begin to give what's sometimes called a paragraph style proof, which is typically what mathematicians do. They don't often produce table style proofs, really, they never do. A paragraph style proof is one in which you simply write out the proof sentence by sentence, paragraph by paragraph. But I think for us, it's a very good idea here at the start to give column style, that is table style proofs, because it forces us to give the justification for every step that we make. Okay. And if you start with paragraph proof, it is very easy to neglect to give that justification. But in the table, if you don't give the justification, that means that your table will have a blank spot, a hole under by. So it will become obvious in that case that the proof is incomplete. So, column proofs. Well, we've talked about those. We'll typically have statements. Well, not typically, we'll always have statements. We'll always have a by column, because under the by column is the justification for each new statement, which is, again, a postulate, a definition, or a theorem previously proven. And we'll also typically have a from column as well, which will tell us the previous lines that we use to reach this new line. Okay, so paragraph later. All right, so here's the first theorem that we will prove together. We will prove that if two angles form a linear pair, then they are supplementary. That is, linear pairs are supplementary. So there it is already in conditional form, so we don't have to translate it into conditional form. I've also provided the diagram for you. So notice that in the diagram, we do have a linear pair. That is the angle ACD and the angle BCD. I tell you what, I'll help you see those. So ACD and BCD. That's our linear pair, and we wish to prove that those two angles are supplementary to one another. Now, what does it mean to actually prove this? And we'll do this together in just a moment. We will produce a diagram, excuse me, not a diagram, a table in column form that takes us from the given to the conclusion, and every step along the way will be justified by some definition, postulate, or theorem. Okay, so let's actually do this. So I tell you what, let me go back and look at this. B, C, B, and D. I tell you what, I will draw the diagram for us so we can have it right in front and we won't have to go back. So we had a diagram that looked something like this. So it was an A and a C and a B, and allow me to check that. So an A and a C and a B and a D. That's exactly right. Okay. And we wish to prove that the linear pair in this diagram are supplementary. Okay, so what's the given here? Then again, a proof always starts with the given. So it's that angles ACD and BCD are a linear pair. Okay, and that is the given. Well, now let's actually develop a proof. And here it's often important, often helpful certainly, to get an idea of how this proof will go. Well, the way that this proof will go is this, is that since angles ACD and BCD are a linear pair, that means that rays CA and CB form a line, of course, which means that angle ACB is a straight angle, which means that it measures, of course, 180 degrees. But CD is a ray through the interior of angle ACB. So, of course, that means that ACD plus BCD is the same as the measure of ACB, which means that that sum must be 180, which means that, of course, it's supplementary. I mean, that's the basic idea behind this, right? We have a line which is 180 degrees, and we have two angles that together, as it were, make that line. So their sum must be 180, which makes them supplementary. So that's the idea that's behind this, of course. But let's get this written up in a rigorous fashion. And when I say rigorous in this class, that just means that we justify every step that we make by some definition, postulate, or previously proven theorem. Okay, so here we go. Here is one way to order it. And when we finish it up, we'll talk about how it is that you could have ordered this differently. Okay, so linear pair. So what does it mean to say that we have a linear pair? It means that the non-common sides form a line. So definitions are super important. You need to know precisely what they say and what they don't say. So a linear pair, in part, that's angle whose non-common sides form a line. So rays CA and CB form a line. That comes, of course, from the given, which is line number 1. And how did we get that out of the given? Well, we applied the definition of linear pair. And of course, you'll allow me to abbreviate DEF for definition and LNPR for linear pair. Okay, so rays CA and CB form a line. Well, what does that mean? That means that angle ACB is straight, of course, right? And how do we know to go from sides form a line to angle is straight? Well, that's definition of straight angle. Okay, and there again I abbreviate. And what do we know about straight angles? Well, we know something about their measure, don't we? We know that the measure of angle ACB is 180 degrees. And why is that true? Well, let me tell you why it isn't true. Excuse me. Let me tell you let me point out a mistake in the attempt to find the reason for this. Sometimes students will say this is just the definition of straight angle. It's not. The definition of straight angle is the sides form a line. Okay, it doesn't say anything about the measure. Well, what does say something about the measure of a straight angle? Well, that's the straight angle postulate. Okay, so straight angle postulate. That says that straight angles measure 180 degrees. Okay, so we've got an angle that measures 180. And of course, we need that 180 to say supplementary at the end. But we also need to say that we have two angles that sum up to ACB. So how are we going to do that? Well, CD, you must say this. Oops, I hate when that happens. So we must say that CD passes through the interior. Through the interior of angle ACB. And how do we know that to be true? Well, that's just our definition of linear pair again, right? So that follows from 1, the given, the definition of linear pair doesn't merely say that the non-common sides form a line. It says they're adjacent as well, and that means that CD must pass through the interior of angle ACB. Okay, so what does that mean then? That means that we can apply the angle addition postulate. So we can say that the measure of angle ACD plus the measure of angle BCD, 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 yep, that's right, plus BCD is the measure of angle ACB. And that comes from line number 5 by the angle addition postulate. What does the angle addition postulate need? It needs an angle and a ray that passes through its interior. And that's what we've got on line number 5. So the angle addition postulate tells us that the two subangles sum up to the whole. Well, what do we know that ACB is? It's 180 degrees, of course. So if ACD plus BCD is ACB, that means that the measure of angle ACD plus the measure of angle BCD is 180 degrees. Okay. Oops. Let me clean that up. It's 180 degrees. And that follows from, well, we needed 2 previous lines to make that happen. We needed both lines 4 and 6. And that followed by the transitivity of equality, which we know that we could also call substitution as well. Okay. And then think about what we've just said. We've said that angles ACD and BCD sum to 180 degrees. And what that means, of course, is that angles ACD and BCD are supplementary. And how do we know to call them supplementary? Well, because we said on line number 7 that they sum to 180 degrees. And the definition of supplementary tells us that when two angles sum to 180 degrees, we may say that they are supplementary. So there is the completed proof. Okay. Now, I did want to point out to you, and I said at the start I would point this out, that this proof could have been ordered differently. That is, we could have started with the line number 5. That could have been line number 2. We could have said that CD passes through the interior of angle ACB, and then we could have done line number 6 after that, and then we could have skipped back up to line number 2. So there was a way certainly to reorder this particular proof. And we'll find throughout this class that there are often different ways to give proofs. Sometimes you can just simply reorder. Sometimes there are radically different strategies that are involved in proofs. And we'll actually see that at the end when we talk about the perpendicular lines theorem. All right, next theorem, T theorem. Prove that if two angles of equal measure form a linear pair, then each is right. Okay, so we'll do this one together, start to finish. And the reason that I want to do this together, start to finish, is because I wish to point something out. It's extremely important and often takes me a little while to convince students of this here at the start. We'll make use of the theorem that we just proved, the linear pairs theorem. That is, the 3 letters LPT will come under the by column, and this is extremely important. Okay, once the theorem has been proven, if we need that result in a later proof, we don't have to go and give the details of the proof again. Instead, we can just give the name of the theorem and thereby use it. Okay, so let me show you how that would work. And this is just the point that I made again. Once the theorem has been proven, we don't have to reprove it later on. We can just simply use it, and we could use it by name. So we actually increase the stock of justifications that we can use, that is, rules that can come under the by column. That grows all throughout the class. Okay, so T theorem, we're going to do this start to finish. So what did we have? We had 2 angles of equal measure that form a linear pair. Okay, so let us draw a diagram to illustrate this as best we can. So, So 2 angles of equal measure that form a linear pair. Okay, so I've got what appears to be a linear pair. And let us say that they are equal in measure. Don't draw into the diagram that those are right angles, because that's what we're supposed to prove here at the start of the proof. We do not know that that is true. We don't really know it until the end, so don't put it in the diagram. The diagram illustrates the given. Okay, and let's label some points here. How about just simply A and B and C and D? I don't know if that's consistent with the way that we labeled the previous proof, but it doesn't have to be. Who cares? It could be FGHI or whatever. Doesn't matter. Okay, so what's the given? Well, the given was that we had a linear pair. That was the first part. So angles ABD and CBD are a linear pair. And we were also given that their measure is the same. So we wish to prove that the measure of angle ABD is equal to the measure of angle CBD. And what we wish to prove is that those angles are right. So angles ABD and CBD are right. Okay, so like I said at the start of the previous proof, it's often extremely helpful to pause and to just think about it before you write it out, to think about why this would be true. And if you can sort of think your way through it, even sort of non-rigorously, then that often gives you a very good clue about how the proof will be constructed. Okay, so we've got this linear pair, right? Which means that the angles are supplementary. Okay, that's the linear pairs theorem, which we just proven. We know that that is true. So we've got two angles that are supplementary. Oh, and they're also equal. Okay, so we've got two equal angles that add to 180 degrees, which means that both have to have a measure of course, 90 degrees. And once we say that they measure 90 degrees, of course, we can call them right angles by the definition of right. Okay, so let's actually write this particular proof out. So I'll construct the table myself. And this is something that you will have to do. So statement and from and by. Okay, so line number 1 is the given. And I tell you what, I've already written what the given is, so I won't take the time to transfer it into the table. I now give you permission to do that as well. If you've stated the given already, you don't have to do it again. So let's see. Okay, so line number 2. Oh, we've got a linear pair. That means we can apply the linear pairs theorem. So we can say that angles ABD and CBD are supplementary. That comes from the given by the linear pairs theorem. You see that? You see that right there? That theorem that we proved previously, it can now come under the by column. We can use it. We don't have to go and recreate all the details of that proof. That would be a crazy waste of our time. Just use the theorem that was proven. As we prove theorems, the stock of rules that can appear in the by column increase. Okay, so what does it mean to say that angles are supplementary? Of course, it means to say that their sum is 180 degrees. We're going to need to do a little bit of algebra here. So let's get an equation. That comes from line number 2 by the definition of supplementary, of course. And then, we know that the measure of ABD is equal to the measure of CBD, right? That's part of the given. So let us do a little bit of substitution here. So instead of ABD plus CBD, we can now write ABD plus ABD again. They're equal, right? So that's 180 degrees. So that comes from, we use the given, which was line number 1, and also line number 3 to substitute. And typically substitution does require 2 previous lines to do its work. And then after this, a little bit of algebra. We've seen this sort of thing before. So we have twice the measure of ABD is 180 degrees. And that follows from 4 by substitution. And then we'll divide both sides by 2. Now, I'll make you a promise. I don't know when I'll actually make good on this promise, but I'll make you a promise that later on we will skip these sorts of very simple and very obvious algebraic details. But here at the start, I wish us to actually give them. Okay, so let us go through all the algebraic details in this. I know this is easy and obvious, but we'll do it anyway. So divide both sides by 2. Okay, so that comes from line number 5 by division, of course. And then we're going to simplify. 2 over 2 is 1. So the left side is simply the measure of ABD. 180 degrees over 2 is 90 degrees. So we simplified, which we call substitution. And then, that'll of course give us a reason to say that ABD, I noticed something up in the proof. I didn't say ABD, so I'll go up and say ABD. That line number 7 will tell us, of course, that ABD is a right angle, but we need to be able to say that CBD is a right angle as well. But we know that ABD and CBD are equal. So if ABD is 90 degrees, CBD is 90 degrees as well. And that's transitivity of equality. And let's see, what lines did we use? We definitely used line number 7. Oh, and we used the given again back up in line number 1. I would call that substitution as well if you like. We know that's true. We've discussed that. And then finally, notice what we can say. We have said that ABD is 90. We have said that CBD is 90. So we can reach our conclusion. We can say that angles ABD and CBD are right. And that follows from lines 7 and 8. We use both of them, and we applied the definition of right. Okay. By definition, a right angle is one that measures 90 degrees. And with that, the proof is complete. Oh, and let me show you something. Here's something that we will do sometimes. We will sometimes at the end of a proof simply write QED. That's not part of the proof. It is not necessary. It's just simply a message to the reader of the proof that the proof is complete, that we set out to do, that we did what we set out to do. That's short for the Latin phrase quod erat demonstratum, which translates roughly as was to be demonstrated. Let me say as well that sometimes we'll also use the box at the end of the proof. Never both. That's redundant. Sometimes we'll use just a box at the end of the proof. That's sort of the modern QED. That's the modern way to indicate that the proof is complete and it has done what it was what we set out to do. All right, so next, the complement theorem. It says that if the non-common sides of two adjacent angles form a right angle, then those angles are complementary. Now, I'll let you do this one yourself on the homework assignment. It's actually very much like the linear pairs theorem, but I thought that I would take a moment just to make sure that you understand what this means, because sometimes students struggle with that statement. It's a bit complex, I know. So what would be the diagram for the complement theorem? Let me go back for a second. It says the non-common sides of two adjacent angles form a right angle. Okay, so it would be something like this. So the non-common sides of two adjacent angles form a right angle. So let me label some points here, A and B and C and a D. And notice that we have an adjacent pair. We have ABD and CBD. Okay, so that's our adjacent pair, right? But their non-common sides form a right angle. Not a line in this case. This is not a linear pair, but the non-common sides, that is raised BA and BC, form a right angle. So that's the picture that goes with that. Okay, so I'll actually let you do the proof of this on the homework assignment. Now, same supplements theorem. It says that if two angles are supplementary to the same third angle, then those two angles are equal. Specifically, and this is to help you out to make sure that you understand, it says that if angle A is supplementary to angle C and angle B is also supplementary to angle C, then the measure of A is equal to the measure of B. I'll let you do this one yourself. This is actually a really important theorem, and we will use it, as a matter of fact, in the proof of the vertical angles theorem. So, vertical angles theorem, here it is, okay? It's this, and this is my favorite theorem of the section for sure. It's my favorite theorem of the chapter. It's my favorite early theorem for the class. And it says that if two angles are vertical, then they have equal measures. The reason that it's my favorite is that, first of all, it's a little bit of a surprise. This is perhaps not something that would have occurred to you when you considered first vertical angles, and I defined that for you. But they are equal, and the proof also, and this is the second reason why I like it so much, the proof is really very pretty. And remember what we said before. We said that theorems already used may be already proven may be used in later proofs. And that actually makes the vertical angles theorem really quite straightforward. Okay, so let's prove the vertical angles theorem. So how do we get vertical angles? Well, we intersect a pair of lines, right? Okay, so let's label some points. So I'll label that point of intersection M, and then I've got an A, and a B, and a C, and a D. Okay, and then let's say the given is this, and then after I state the given, I'll have to make a point about it. So angles AMB and CMD are vertical, and what we wish to prove is that their measures are equal. So the measure of angle AMB we wish to prove is the same as the measure of angle CMD. Okay, now notice what we have not said, right? We have not said that the other pair of vertical angles present in this diagram, that is angles AMC and BMD, top and bottom as it were, are also equal. But what I say to you is that the proof that we give for the equality of the left-right vertical pair will be exactly similar in structure to the proof of the equality of the top-bottom vertical pair. So if we can prove it for that one pair, it's just pointless to prove it for the other pair. That would just be simple repetition. Okay, pointless repetition, perhaps better to say. So we will do it for this one vertical pair, and then the same structure of proof, the same form of proof will work for any vertical pair. Okay, so let's think about these two angles, okay? The angle AMB and CMD. We wish to prove that they're equal. Notice that they both form a linear pair with angle AMC. Okay, so look at angle AMC. Each of those angles forms a linear pair with AMC. And then by the linear pairs theorem, that means that each is supplementary to AMC. Oh, but then we have two angles each supplementary to the same third angle, and that means, of course, that they are equal. And that was the same supplements theorem. So actually, in this proof, we will use two previous theorems. We will use the linear pairs theorem, and we will also use the same supplements theorem. Okay, so once again, I'm not going to recreate the given. That's the given from up top, right? And then, well, what do we need to say? Well, we need to point out, first of all, that angles AMB and CMD, and I tell you what, I'm going to stretch this out just a bit so I have room to do everything. So allow me to move the from and the by. I should have known that at the start. Okay, so from and by. So angles AMB and CMD form a linear pair. Oh, no, I said that wrong. I got distracted by my need to change the table. So it's AMB and AMC. Yeah, and it's AMC. Sorry about that. You got to be really careful when you do your proofs. You have to be careful about the names of the angles involved. It's easy to get them wrong. So AMB and AMC, they definitely form a linear pair, right? And we also have another linear pair as well. So angles CMD and AMC also, I'll perhaps add, form a linear pair. And how do we know this to be true? Well, of course, it comes from the given. And how did we get here? Well, we applied the definition of linear pair to the diagram as given, right? We know that in the diagram we have a pair of lines that intersect, so of course we have linear pairs. All right, so what comes next? Well, what do we know about linear pairs? Well, we know they're supplementary, and that's by the linear pairs theorem. So angles AMB and AMC are supplementary, and also angles CMD and AMC are supplementary. Okay. And notice what I've allowed myself to do here. I've allowed myself to write multiple lines, multiple statements on each of these lines. And the reason that I can do that is because each of those statements follows from the same previous line by the same rule. So you could break them up into multiple lines if you like, but it's not really necessary. So each of these statements on line number 3 follows from line number 2 by the linear pairs theorem. And don't you dare tell me that that's the definition of supplementary or the definition of linear pair or anything like that. What says that linear pairs are supplementary is the linear pairs theorem and nothing else. Okay. Now, look at what we have on line number 3. We have two angles, namely AMB and CMD, that are both supplementary to the same third angle. And what do we know about two angles that are supplementary to the same third angle? They are equal. So the measure of AMB is equal to the measure of angle CMD. Okay, and that follows from line number 3 by, here it is, the same supplements theorem. Now, notice how short that proof is because we allowed ourselves to make use of previously proven theorems, specifically the linear pairs theorem and the same supplements theorem. It would be crazy not to do that. It's just the redundancy to have to prove the theorems again, and it also makes our proof so much easier to write and to understand. Okay. Now, if you were actually to, in the course of this proof, do all the work necessary to reprove the linear pairs theorem and the same supplements theorem, well, I mean, that would be correct, right? I wouldn't count it incorrect if you made the proof unnecessarily wrong, but I would definitely point out to you that it was unnecessarily wrong. And it's honestly just a waste of your time. The proof of the linear pairs theorem can be 4 lines long, just like this. Oops, and let me indicate that the proof is complete. So I tell you what, I'll use the box because that's what's most commonly used. If you like QED, you can use QED. Okay, so final theorem. We're not going to do this one together, but I thought we would talk a little bit about it. So it's the perpendicular lines theorem, abbreviated PLT. Then it says that perpendicular lines intersect to form 4 right angles. And this is not the definition of perpendicular lines, okay? So the definition says that perpendicular lines form at least 1 right angle. It doesn't say that they actually form 4. They do, as a matter of fact, form 4, but that's not true because of the definition. It's true because we can prove it. Okay, so here's a diagram. We've got 2 lines that intersect. They make 4 angles, of course, and we assume that at least one is right. And we'll call that one that we know is right, angle 1. So there's the given. M perpendicular to 1 with angle 1 right. That's the one we know is right. And we wish to prove that the other angles are right as well. Okay, so let's talk a little bit about the strategy here. And I'll go back to the diagram here in a second. But there are multiple strategies, like it's said in that next slide, that one can pursue. So I thought that we would talk about these just a little bit. Okay, so here's one strategy that you might pursue. Consider angles 1 and 2. Okay, angles 1 and 2. What are they? Linear pair. What does that mean about their sum? Well, it means they're supplementary, and so their sum is 180 degrees. But the measure of angle 1 is 90 degrees. And so what does that mean that the measure of 2 has to be? Well, it would have to be 90 degrees as well. Oh, so we now know that the measure of angle 2 is also 90 degrees, which means that it's right, of course. Now, consider the relationship of angle 2 to angle 3. What are they? Oh, they're also a linear pair, which means that their sum is also 180 degrees. But we know that the measure of 2 is 90, so that leaves 90 for 3, and so on. Now, let me say something to you now. And this is something we'll have to come back to and something that we will emphasize. But it's a point that's come up before. If we've ever done something before, we will not force ourselves to do it again. Okay, so once we've proven that angle 2 is a right angle because it forms a linear pair with the right angle 1, then we will not actually go through. There's no need to actually go through and prove that angles 3 and 4 are right angles if you intend to do it in the same way, okay? Because it's precisely the same structure of proof, right? So we'll know that 2 is right, but 2 and 3 are a linear pair, so 3 will be right. But we already did that with 1 and 2. So here's something that would be perfectly acceptable, okay? Prove, go through do the work necessary, give all the details to prove that angle 2 is also a right angle, and then say something like, and then in the same way, we could also prove that angles 3 and 4 are right as well, which is perfectly true, and I give you permission to do that. If the rest of the proof will look structurally exactly like the first part of the proof, you have permission to say, and we may complete the proof in the way that we have already seen. Okay, so that's one way to do this proof, just, with linear pairs. There's another way to do it as well. Okay, so let us say that we prove, well, that also uses linear pairs, but only once and then uses something else. So let us say that we prove that angle 2 is a right angle because it forms a linear pair with the right angle 1. Well, what's the relationship of 1 to 3 and 2 to 4? They're vertical angles, of course, right? And what do we know about vertical angles from the vertical angles theorem? Oh, they're equal. So if angle 1 is right, angle 3 must be right. And if angle 2 is right, angle 4 must be right. So we could start with a single instance of the linear pairs theorem to get that angle 2 is right. And then we could use make use of 2 instances of the vertical angles theorem to get that angles 3 and 4 are right. Okay, so there's 2 basic strategies that one can pursue here. And again, it's this. Just use the linear pairs theorem all throughout to get angle 2 right, then angle 3 right, and angle 4 right. And you can use that shortcut where once you've done it the first time, you don't have to do it again. Or second basic strategy, make use of the linear pairs theorem once, and then use the vertical angles theorem twice to get that angles 3 and 4 are right as well. So that's really a very important idea. As we work our way through this class, there will often be different strategies that one can adopt to prove certain theorems. And the deeper we get into the class, well, sometimes we'll find that there are radically different strategies that can be used to prove a theorem. So one ought not to come away from this section with the idea that there is always one and only one way to prove a theorem. That is false. There are often many, many ways to prove a theorem. Some perhaps better because they're shorter or more easy to understand, but still multiple ways to do it.